Stanford University.
Good evening, everybody. Pleasure to see some of my old friends and possibly some new people. Tonight we have the pleasure of having one of our colleagues at SITP. Oh, incidentally, I'm Leonard Susskind. I'm the director at SITP. We have the pleasure of having Steve Kivelson, who is one of our professors, but more than one of our professors. He's one of the leading condensed matter physicists in the world. Expert on, well, I won't even go through the things that he's an expert on. Member of the National Academy, winner of important awards, which I won't go through. One of the things I just found out today is, Steve, I discovered that you are a student of Julian Schwinger, so I wanted to ask you, have you ever met him?
My mother was a student of Julian Schwinger's.
Oh, it says in the...
I was a student of my mother, and so by the transitive property.
Well, if you go and you look at the list of Harvard alumni, PhDs, it says that you were a student of Julian Schwinger.
Okay, I accept.
So again, I ask you, have you ever met him?
Yes. I've even taught him a thing or two.
Okay.
About skiing.
Driving fast cars? Okay. Steve is going to tell us about superconductivity, and he's a theorist, a very outstanding theorist, but he's going to do an experiment, I think. Is that right?
Well, a demonstration.
We're going to
Yes.
try it. Okay.
Good. This talk is scheduled for 2 hours, and that seems like a cruel and unusual punishment.
Right.
So I'm planning on talking for an hour, but since we have time, if people want to interrupt with questions or comments, please feel free to do so. This is the first of 2 lectures, and let me tell you what I want you to come away with at the end of this lecture, and mention also what I want to cover in the next lecture. So, lecture 1, I more or less want to explain the title of these lectures. I'm going to tell you what superconductivity is. And I'm going to tell you what macroscopic quantum phenomena are. And I'm also going to try to explain a broader philosophical notion as it pertains in physics, the new notion of emergent phenomena. In physics. There are a number of other things that I'll allude to as we go through. I'm going to try to give you a taste of the reverence with which we discuss fundamental constants of nature, how much you can learn just by thinking about the meaning of the fundamental constants of nature. I'm going to, along the way, discuss what resistance means in normal conductors and what dissipation has to do with resistance. I'm going to talk a little about magnetism and explain to you that magnetism is always a quantum mechanical phenomenon, so it's always quantum magnetism. And I will introduce you to the second and third laws of thermodynamics and to the distinction between precision and accuracy. That's the first lecture. The second lecture I'm going to first talk about the microscopic origins of superconductivity. That is to say, what are the electrons really doing? I'm going to talk about something called high temperature superconductivity. We'll actually see high temperature superconductivity today. My advertised demonstrations will take advantage of high temperature superconductivity. In this context, high temperature means such balmy temperatures that air is still a gas. And I will turn on the philosophical side to tell you what we mean by a paradigm shift in physics. And along the way, I hope to introduce you to some specific history of the discovery of superconducting materials, and to conclude by telling you a little about the frontiers in superconductivity research, theories of high temperature superconductivity, and notions of macroscopic quantum coherence, which are the ideas that allow us to do experiments on Schrodinger's cat in the laboratory. All right, so that's the goal. Nobody's interrupted me yet. I'm very disappointed with this audience. So let me first talk about ordinary conductors. So ordinary conductors are characterized by their resistance. And actually, I thought that I might have a history board over here. The history of the ideas and the nature of the ideas themselves are two completely separate things, but it gives a little bit of human drama to the narrative to at least make some mention of history. And so here, the two important notions are Ohm's law, which was published by Ohm in 1827, and Joule heating, which is Joule 1841. And so Ohm's law is probably a piece of physics that most of you have encountered. It says that if I have some sort of metallic wire and I apply a voltage and measure how much current flows through the wire, that the amount of current is proportional to the voltage, or the voltage is proportional to the current. According to Ohm's law, V equals IR, where R is the resistance of the wire. And this is also related to the rate at which energy is used up, in which power is dissipated. And this is Joule's contribution to this, which is R times I squared. So the more current I try to drive through the wire, the more power it takes. The bigger the resistance, the more power it takes. The smaller the resistance, the less power it takes. And so, of course, for power transmission, we would like power transmission lines with as little resistance as possible. Now, the resistance isn't an intrinsic property of a material. Clearly, if my wire is longer, the resistance will be bigger. And if my wire is bigger across, there are more places for the current to go. So the resistance in general, I expect to grow linearly with the length of the wire, to drop linearly with the inverse of the cross-sectional area of the wire. And the proportionality constant is something called the resistivity. And the resistivity is an intrinsic property of a material. So the resistivity of copper at room temperature is some number that one can look up. And similarly, the resistivity of lead. This is a property of the material. And so since I study materials, this is the quantity that I'm interested in. Now, there is a distinction that we make, a broad distinction between two types of materials. There are materials that we call metals, and there are materials that we call insulators. And this distinction is based entirely on the value of the resistivity. The resistivity of metals is small, and the resistivity of insulators is big. If you look it up on Wikipedia, it tells you that the resistivity of metals is 10 to the minus 6 ohm centimeters. Okay, of course, different metals have different resistivities, but that's what they mean by small. And for insulators, they say the resistivity is 10 to the 16th ohm centimeters. That's big. Let me be, in fact, explicit. If we look at graphene, which I think at room temperature is the world's winner on resistivity, its resistivity is indeed 10 to the minus 6 ohm centimeters at room temperature. And if we look at Teflon, its resistivity is as big as 10 to the 25th ohm centimeters, which means that the ratio of the resistivity of Teflon to the resistivity of graphene is equal to 10 to the 31. Okay, so there's a very, very big difference in the resistivity of insulators and metals. You know, it's hard to understand what big numbers mean. So I tried to find another big number to compare this to. So I, for instance, thought of the number of stars in the universe, and at least according to Wikipedia, that's a measly 10 to the 29. So this is 100 times bigger than the number of stars in the universe. Now, for physicists, that's not, I mean, there's obviously a big difference between metals and insulators, but we'd really like an idea of big or small compared to what. And here's where fundamental constants of nature come in. I can invent something which I'll call the quantum of resistivity, which is a quantity that has the units of resistivity that I can make out of fundamental constants of nature. So the fundamental constants of nature, all of which we're going to return to later in the lecture, are Planck's constant, which is the fundamental constant that determines the quantum nature of processes, the charge of the electron, and the mass of the electron. And the conventional definition here has a factor of 2 pi squared, just because, since we're talking about many orders of magnitude, that 2 pi squared doesn't matter. And this number turns out to be 135 times 10 to the minus 6th. So why did I say that? 1.35 times 10 to the minus 4th ohm centimeters. So small or big means compared to the quantum of resistivity. And so metals are materials that have resistivities that are very small compared to this number, and insulators are materials that have resistivities that are very large compared to this number. All right, so good. What determines the resistivity of metals? We're going to be interested in metals because ultimately we're going to be interested in even better conductors than metals. We're going to be interested in superconductors. So it doesn't make much sense to compare them to insulators, which simply can't conduct. We'll compare them to things that can conduct, namely metals. And so we might ask ourselves, what do we know about the resistivity of metals? So the first thing that we know is that the resistivity is greater than or equal to 0. Okay? We know this as a consequence of the second law of thermodynamics. The second law of thermodynamics is technically the law of increase in entropy, but in more colloquial terms, it's that you can't win. If we could find a material that had a resistivity that was less than 0, well, we could solve all energy needs. We would just drive currents through it, and then we would drive motors with that. Maybe I've got a date here. I'll put it on my history board. Where's my date for the, lost it. I don't remember the date of the second law of thermodynamics. All right, long ago. The second thing is more empirical and more to do with materials, which is that the resistivity of a metal is a function of its temperature, and it's a function of its purity, and maybe some other things. And there are two features of this general dependence that are worth noting. One is that the resistivity of pure crystals is less than the resistivity of dirty crystals. So somehow the more crystalline, the more pure, the more perfect the metal is, the lower its resistivity. And the second thing is that the resistivity is an increasing function of temperature. What this equation says is the derivative of the resistivity with respect to temperature is positive. That means as you heat a system up, it becomes more resistive. And conversely, what this means is that as you cool a system down, it becomes less resistive. So this has been known for a long time, but it led, in particular, maybe the father of low temperature physics, Camerlé-Onnes, to ask the question, well, what would happen if I made a crystal really pure and I cooled it to absolute 0? What would happen to the resistivity? So let me just take a minute. I mentioned this funny word, absolute 0. So this is a notion that was developed before quantum mechanics. The idea was that if we looked at a gas, then the average kinetic energy per particle is proportional to the temperature. And so as we lower the temperature more and more, the molecules of our material start moving less and less. And if we extrapolate this, there becomes a temperature at which they would stop moving altogether, that would be the lowest possible temperature. Temperature scales like Fahrenheit and centigrade are somewhat arbitrary, but this would be a temperature that has an unambiguous physical meaning as the lowest possible temperature where everything stops. Now, the notion of absolute zero survives quantum mechanics, but it becomes a somewhat different notion in quantum mechanics, and that's because of the uncertainty principle. So the uncertainty principle, which is, as we all know, one of the central tenets of quantum mechanics, which was introduced by Heisenberg, tells us that if we have a particle of mass m, then the kinetic energy, mean kinetic energy of that particle, times the mean squared distance over which I allow it to move, must always be bigger than some number times this fundamental constant of quantum mechanics, Planck's constant squared. And so obviously, as I cool down my material, it's going to condense. It's probably going to form a crystal. If it forms a crystal, the atoms aren't moving around over very large distances, so delta R is going to be small. And if delta R is small, and if the mass of the particle isn't infinitely big, then the kinetic energy of the particles can't approach zero. It approaches a minimum value. And so in quantum mechanics, what we find is that the system approaches its ground state, an essentially unique quantum mechanical state of the system, as t goes to zero. And the formal statement that corresponds to this is that the entropy of the system goes to zero as t goes to zero. And that is the third law of thermodynamics, and this is a fundamentally quantum mechanical contribution to thermodynamics. It also has the consequence, when combined with the second law, that absolute zero can never be reached. Because if the entropy of the universe has to always increase, and if at zero temperature my system would have zero entropy, then I can't reduce its temperature by having its entropy go somewhere where its entropy would be even lower. So this idea of asking what happens to the resistivity at zero temperature is an abstract notion. We realize we're not going to actually be able to do a measurement at zero temperature, but nonetheless the idea that Camerleonis had is let's lower the temperature lower and lower and extrapolate the answer to zero temperature and see what happens. So as I said, Camerleonis was the father of low temperature physics. He liquefied helium, which is below its boiling temperature of something or other. 4.13. 4.13 degrees Kelvin. This, by the way, is interesting. It's an interesting quantum mechanical effect. In general, when we take materials and cool them down, sometimes they form liquids, but eventually when we cool them down enough, they always form solids. They crystallize. The atoms are moving so little that they form a solid in which the atoms stay put where we put them. Helium is the one counterexample to that. In helium, the quantum zero-point motion of the atoms, the fact that the kinetic energy times the displacement can never be small, and since the mass of the helium is small compared to other elements, it turns out that helium at atmospheric pressure remains liquid all the way down to zero temperature. Okay, so at any rate, this discovery has to do with having built the world's best refrigerator. And then he put a very clean metal, which in this case was mercury. Because mercury remains liquid, it's very easy to purify and to crystallize into nice crystals. And what he discovered was that when he measured the resistivity of mercury as a function of temperature, indeed, it decreased as he lowered the temperature. And then, to his astonishment, at a particular temperature, it dropped to zero. So in this case, this temperature was 4.2 Kelvin, and this is minus 452 Fahrenheit, for those of us who might think that that was balmy. Okay, now, I said something non-scientific here. I said that the resistivity is equal to 0. Now, the integer 0 is a perfectly physical quantity. I can have 6 apples, or 3 apples, or 0 apples. There's no ambiguity there. But 0, the real number, is an abstraction. In physics, we talk about things that we can measure, and so 0, the real number, is not something we can measure. So I need to tell you what I mean by 0. So the best way to measure 0 is by measuring persistent currents. So let me go back to this board for a moment. Not this board. This board. And say something else about resistivity. So suppose I have a metal and I drive it in some way by attaching it to a battery or rotating it in a magnetic field as in a generator, and then at some point I stop driving it. Now, Ohm's law tells me that ultimately the resistivity, the current, is going to be 0 if I'm not driving it. But this won't happen instantaneously. I have a current flowing, and so there will be some time scale over which that current will decay to 0. That's a time scale that characterizes the dissipation of the system. It characterizes how the entropy of the system increases, and this nice organized state that we have with the current flowing decays. And so we can ask, how fast does the current decay? Well, and the answer depends a little on what sort of circuit one is looking at. There's a time called the RC time, which is the resistance times the capacitance. There's a time in purely inductive circuits, which is R divided by the inductance of the circuit. But in general, what we see is that the time that it takes for the current to decay is going to be proportional to the resistance. So in a persistent current experiment, what we're going to do is rather than directly measuring the resistance, we're going to ask, how fast does a current decay? So what we're going to do is we're going to take a ring, maybe of mercury, below 4.2 Kelvin. We're going to get a nice current going through it. If we have a current going in a ring, then we know from elementary electricity and magnetism that that means there will be some magnetic flux through the ring. And then what we're going to do is we're going to measure this current as accurately as we can. Or actually, more precisely, what we do is we measure this magnetic field as accurately as we can. And then we go away, and we leave this ring at a temperature below its critical temperature for as long as we have patience. And then we come back and we measure how much that current has decayed. And the answer is 0, which is to say, within the accuracy with which we can do the experiment, we cannot detect any decay of the current. And so based on that, we can ask, what is the longest lifetime this current could have and still escape detection in our very careful experiment? And the answer is, well, tau is much longer than the life of the universe. Okay, so while this 0 was a little bit of a lie, that's a pretty serious 0. Yes?
Does it take energy to switch the direction of the current?
So the current is going to, I have to prepare this system this way. So there are several ways I can do it, but the most obvious is, let's start with this magnetic field through this ring, and at a temperature above this critical temperature. And then, so I have this thing sitting in a magnet, and then I cool the system below this temperature, and then I take it out of the magnet. And now the current is going to be going around, and the magnetic field is going to be there. Now, in fact, that's not the lowest energy state of the system. The system would be happier having no magnetic flux through it. This magnetic flux is trapped through the ring. The price the system has to pay is that it has to have a current going around, and currents cost energy. But in this superconducting state, there is no way for this current to decay. So it stays there forever, or at least for the life of the universe. Okay?
Question.
Yeah. Was there another question?
Yeah.
Yes.
When you actually go to measure this, I presume you have to suck some energy out in order to...
No, actually, that's one of the nice things about magnetic fields, is you can measure them without any energy involved. Good. Are there other questions? Yeah. Now, this is really striking. As long as I keep this ring below 4.2 Kelvin, this magnetic field sits here forever. And the moment I heat it up above 4.2 Kelvin, the magnetic field's gone. Seconds. Yeah.
Does forever really mean forever?
Well, I'll actually compute how long it is.
Question.
Yeah.
Are there limits on how big that current could be?
Yes. So there is a critical current, and if you try to make the current exceed the critical current, all sorts of bad things happen. Yes?
Does it generate heat?
No. So I can't, this is a completely quantum mechanical effect. The system sits there forever. If it generated heat, then it would need some source of energy to keep it going. So this is really quite an extraordinary observation. Good. So I think on this board, I'm going to start keeping track of what we've learned about superconductors. So one thing is they occur below some temperature called the critical temperature. Another thing is that they support persistent currents. Now, at this point, I want to take a detour to talk about emergent phenomena. So, picture having an extremely good microscope so I can really zoom in and look at what the electrons are doing in this mercury wire. And so I'm at 4.3 Kelvin. The electrons are mighty quantum mechanical. They're moving around. They're scattering off of each other and off of other things in the material. I look at them, and okay, it's complicated, but they're electrons. They're moving around. They're doing some sort of quantum mechanical dance. And now I cool a little bit below, say to 4.1 Kelvin. And I look at the electrons, and to tell you the truth, you can't tell the difference. They're a little colder. But it's not going to look any different to me than going from, say, 4.4 Kelvin to 4.3 Kelvin. Now, in fact, resistance is something that is very natural if we think about the motion of electrons. I accelerate an electron in an electric field, it accelerates, and then it bumps into something and scatters and then forgets what it's doing and starts over. So that's how electrons move through metals. In fact, it's sort of surprising, you know, the electrons in a metal, they're atoms all over the place, and somehow the electrons manage to move very long distances if I have a good metal. They propagate long distances before scattering, and that's why the resistivity of metals is small compared to the quantum of resistance. Okay, this is actually in itself a remarkable quantum mechanical phenomenon. It was explained by this man up here, Felix Bloch, and that's a quantum mystery for another day. But somehow or other, in a superconductor, how can it be that the electrons are moving through the metal, they're scattering like mad, just like they were before, and yet the resistivity is zero? Okay, so this is an example of an emergent phenomenon. What's an emergent phenomenon? An emergent phenomenon, well, if you look it up on Wikipedia, there's a multi-page article which is actually quite interesting. It talks about emergence in philosophy, in science, in computer science, in art. There's a lovely book by one of my colleagues, Bob Laughlin, called A Different Universe, which is all about emergence. But the notion is very simple. The notion is that if I have a collection of many simple constituents, in this case, many electrons, each of which are simple objects whose quantum mechanics I understand, but if I put together a large number of them, then the collective behavior of the composite, the behavior of the crowd, not the behavior of the individual, can be entirely different from the behavior of the individuals. In physics, of course, we want to have a precise definition of what we mean by this. So what we mean is, by an emergent phenomenon, is a phenomenon that cannot be understood by studying any finite number of particles. It's a property that emerges only in the limit that the number of particles tends to infinity. Okay, so good. That's an emergent phenomenon. I told you that I have a ring of metal in the laboratory and that the current lasts forever. But, of course, there are a finite number of electrons in my ring. So again, I must have been lying to you. Forever could only be a property of the system in the limit of an infinite number of particles. And for a finite number of particles, it just must be a really long time. And indeed, we can estimate that. The time for the decay of this current should go like some microscopic time that really won't matter to us, times the exponential of two large factors. One is the radius of this ring divided by a microscopic length scale, which is of the order of the radius of an atom. And the other is 1 over the temperature divided, a microscopic energy scale divided by the temperature, where this microscopic energy scale is on the order of the binding energy of hydrogen. So if we, for instance, looked at a ring with a characteristic width of 1 millimeter at a temperature of 1 degree Kelvin, this would go like T naught to the exponential of 10 to the 12th. Okay? Now, this is really a big number. So when I was growing up, I was told that the biggest number was a googol. This was before Google meant something else. A googol is 10 to the 100th. Okay, this is really a lot bigger than that. Okay, then people thought that a googol wasn't big enough, so they invented a googolplex. And a googolplex is 10 to the googol. And that, indeed, is bigger. Okay, so this time makes the life of the universe seem like a split second. And indeed, as the number of degrees of freedom here goes to infinity, this time really becomes infinity. All right. Good. What else? Well, actually, I wanted to add another date to my history board. Oh. Discovers superconductivity. That's an important one here. That's 1913. This is 1911. The next really fundamental experimental discovery was the Meissner effect, which is 1933. And that's such an important effect that it also goes on this board. And what the Meissner effect is the expulsion of magnetic field. The Meissner effect is a statement about the superconducting state, which we've already illustrated here, which is that magnetic fields are expelled from superconductors. So the reason this magnetic flux can't get out is because to get out, it would have to pass through the superconductor. And the superconductor expels magnetic fields. It forbids the magnetic field from entering it. All right. I'm not going to be talking about the theory of superconductivity, But since I'm talking about history here, let me put in an important point here, which is that from the discovery of superconductivity, it was understood that this must be a new and extraordinarily interesting quantum phenomenon. But it remained a puzzle unsolved until BCS in 1957. So BCS is Bardeen, Cooper, and Schrieffer. And although I was not, in fact, a student of Julian Schwinger's, I was, in fact, a postdoc of Bob Schrieffer's, S. B here, Bardeen, is the only person to have won 2 Nobel Prizes in physics. One was for solving this profound and long-standing problem in theoretical physics, the theory of superconductivity, and the other was for inventing the solid-state transistor. So he should, in fact, be the patron saint of Silicon Valley. But that's not that there was nothing going on here. All of the greats tried to understand superconductivity. There were papers by J.J. Thomson, Albert Einstein, Niels Bohr, Felix Bloch, the same Felix Bloch, Werner Heisenberg, Max Born, Richard Feynman. And there's actually a very nice paper that I recommend to you called Failed Theories of Superconductivity. It's actually a take on the history of science that's not usually pursued. It's very respectful. This was a hard problem. It's no shame that these people failed. The author is Georg Schmelian, and you can find it on the internet by looking for the archive. The archive is a website where physicists post their papers and share their ideas instantly. It's one of the great sociological developments in our field, and the number of this is 0447, volume 2. I also, at this stage, owe you an apology. In my abstract, I boasted that this was a quantum mystery that Einstein had failed to understand. This is an entirely true statement, but also entirely irrelevant. It was purely advertising. I've been told that if you say Einstein, then people will come.
How about Hawking? Did he fail too?
You know, he came along too late. Good. Good. Well, maybe I'm going slower than I thought. So I'm going to skip the next thing and yeah.
Do you have to?
What?
What was the next thing?
Well, I was going to discuss. Okay, I'll do it. I can do it quickly. So I'm going to be talking. I've already been talking about magnetic fields and magnetism. So let me make an interesting observation here. I've been telling you all along that superconductivity is an interesting quantum mechanical phenomenon, but I've never really backed that up. Now, in fact, all magnetic properties are quantum mechanical properties. It's easy to prove that in classical physics, thermodynamic properties that is to say, all properties of systems in equilibrium, systems like this, are independent of the magnetic field. So any magnetism you see, superconductivity, but also ferromagnetism, are intrinsically quantum mechanical properties. So if you want to see quantum mechanics in your hands, just look at magnetism. In fact, magnetism is not only a quantum mechanical property, it's also a relativistic property. So magnetism depends on h, the fundamental constant of quantum mechanics, and c, the speed of light, the fundamental constant of relativity. And all magnetic effects vanish if either h goes to 0 or if c goes to infinity. Now, okay, that you'll have to take my word on, but let's try to get a little bit closer. Let's see if we can actually imagine measuring something in our superconductor that depends upon Planck's constant. Then we'll know that we're seeing a quantum mechanical effect. So if I think about magnetism, I immediately want to construct something, some object that I can look for, that I make the way I made the quantum of resistance out of fundamental constants of nature. And there is such a quantity. It's called the quantum of magnetic flux. And it's the product of Planck's constant, the speed of light, and it's divided by the charge of the electron. And this quantity is the fundamental quantum of magnetic flux. So soon, where's my history board? Here's my history board. So where's my history sheet? I don't know my dates, so I need my history sheet. What did I do with my history sheet? Good. This is a piece of the history in which we can take some hometown pride. There were experiments done by Little and Parks and by Deaver and Fairbanks, all at Stanford, which discovered that in a superconductor, the flux, the magnetic flux, the amount of magnetic flux that's going through a ring like this is quantized. It's always an integer times something called the superconducting quantum of flux. And the superconducting quantum of flux is 1/2 the fundamental quantum of flux. It's hc over 2e. That 2 is an important clue concerning the origin of superconductivity, and that 2 will be one of the things I'll talk about a lot in my second lecture. And this is, what? This is 1962. I'm not going to actually talk about flux quantization. I'm going to talk about an even more direct and spectacular proof that superconductivity is a macroscopic quantum effect, which is something called the Josephson effect. This is where things get good, because here is a place where the theorists were ahead. The Josephson effect was predicted in theory and then later discovered in experiment. What?
Graduate student.
Josephson was a graduate student, that's right. So here, we'll go on the history board, the Josephson effect was predicted in 1962 and was observed by the great experimentalist Phil Anderson and Rowell in 1963. And what the Josephson effect is the following. We take a superconducting wire and make a narrow junction and then have another superconducting wire. Now, because the superconductor has zero resistance, I can't put any voltage across it. If I put a voltage across it, an infinite amount of current would flow. But since I have a junction here, it's possible to put a voltage across it. So we put a voltage across this junction and ask what happens. And what happens is quite remarkable. We put a constant voltage. There is no time dependence here. We put a constant voltage, and what's found is that a time-dependent current, an oscillatory current, results. So it oscillates periodically in time, and this frequency satisfies the Josephson relation. Planck's constant times the frequency is equal to 2. That's the same 2 we encountered before, times the charge of the electron times the voltage. Right? So here, these are devices we can hold in our hand. These are macroscopic devices. We measure the voltage with a voltmeter. We measure the current, well, notionally with an ammeter. We measure the frequency at which the current is oscillating, and the relation between the voltage and the frequency involves Planck's constant. Now, by now,
Is this independent of the gap?
what?
Is this independent of the gap size?
Yes. The amount of current depends upon the gap size, but the frequency doesn't. Now, by now, I think you are probably sufficiently alert that you might say, what do I mean by equals? After all, this is a real number that I measure, and this is a real number that I measure. What does equals mean? So I'll tell you what equals means. So first place, I can tell you what it means in terms of precision. So what we do is we take two different Josephson junctions, we put the same voltage across them, and ask how similar is the frequency with which they oscillate. And, well, to the best that we can measure, they oscillate at exactly the same frequency. And then we ask ourselves, suppose they differed by the most they possibly could, what precision do we know the frequency with? And so we know the frequency better than 1 part in 10 to the minus 17th. Okay, so in terms of precision, that's the same as knowing the US GDP to the nearest hundredth of a cent. Okay? Now you can ask me, to what accuracy do we know this? And the answer is, it's exact. And the reason it's exact is that this is the definition of the volt. So this is one of the crowning discoveries of my field of solid state or condensed matter physics. This is a quantized macroscopic phenomenon. There are a few other such phenomena, such as the quantum Hall effect and the fractional quantum Hall effect, but this one looms high as one of the most beautiful phenomena in condensed matter physics. Good. Let me discuss one more. So, suppose I take a piece of superconductor and I apply a magnetic field to it. And so if the magnetic field is small, then I know, because of the Meissner effect, that the magnetic field will be expelled. And this will cost energy. So the system will do it because it likes being a superconductor, and it can only be a superconductor if it doesn't have any magnetic field. But at some point, if I turn up the magnetic field enough, the system's going to say, enough is enough. I'm going to kill the superconductor and let the magnetic field through. No more superconductor. But there are two ways that the system can evolve between these. And these two ways are so different that we call superconductors either type 1 or type 2, depending upon which way they go. So one is, it can all happen at once. We turn up the field until H equals some critical field. This is actually related to the question somebody asked about how big of a current can you support. So in order to expel this field, currents have had to flow around the outside of the system, and at some point those currents are too much to support, and the system goes normal. It becomes a metal. So this is type 1 superconductors. But in type 2, the system first goes into a sort of compromise state. It goes into a state that sort of looks like this. What it does is it kills superconductivity in a few places. And then the magnetic field can't go through the superconductor everywhere, but it goes through in these little holes. And actually in these little holes, each one of them has an amount of flux which is equal to the superconducting flux quantum. So the number of these little holes that the system makes is proportional to the strength of the magnetic field. And these little holes then get stuck on impurities, and so once we've set up this state, just like here when we put flux through a macroscopic hole, that stayed there forever. So here, if we set this up like this state will stay for a really long time. Now that allows us to make our demonstration. That allows us to produce magnetic levitation. So what happens is that this is liquid air, liquid nitrogen. It's even cooler than superconductivity sometimes. And what I have in this little container is a piece of a superconductor. It's a piece of a high temperature superconductor, which, as I told you, is superconducting at temperatures where air is still a gas. So by pouring liquid air on it, I'm cooling it below its superconducting transition temperature. At least I'm trying to. Okay, good. Now, this track here is a bunch of magnets, ordinary magnets. And so there was a lot of magnetic fields going through this when it was in its normal state. So they're still going through it when I've cooled it into its superconducting state. But now that it's in its superconducting state, it's going to fix that amount of magnetic field. So if I pulled it up or pushed it down, so it would be in a place, an environment with a different amount of magnetic field, it's going to be unhappy. So rather than doing that, it's going to stay at the same height. Okay, so that's a type 2 superconductor. In fact, and now let's see one other thing. So again, we've cooled it down below its superconducting transition temperature, and so it levitates. But eventually this nitrogen, this liquid nitrogen, is going to burn off. Boil off, not burn off. Let's dump it. Here we go. And so now this thing is going to start heating up, and at some point, not yet, but at some point, still not yet, but at some point, it's going to heat up above its transition temperature, which you can see it's starting to do, and then
It's time.
so I will talk for another few minutes, and then I'll invite you down to play with the superconductors by yourselves. So let me summarize. So what I've done is I've explained to you what superconductivity is. Superconductivity refers to a distinct state of matter. It occurs below a certain critical temperature. It is as different from a metal as a gas is from a solid. It is characterized by a number of remarkable macroscopic quantum phenomena, persistent currents, the Meissner effect, the Josephson effect, and of course, magnetic levitation. It is an emergent phenomenon It's a property of the electrons in the metal which cannot be understood by understanding the dynamics of any finite number of electrons. It's a macroscopic quantum phenomenon in the sense that measurable quantities are related to each other by factors of Planck's constant. So next week, I will discuss a little of what the theory is, how we understand the way the superconducting state emerges from the interactions between electrons. I will discuss high temperature superconductivity. If high temperature superconductivity had not been discovered, well, I can't pour liquid helium, and so we wouldn't have been able to do a demonstration. And I'll talk a little about the brutal intellectual wars that took place following the discovery of high temperature superconductivity, as people understood that while the BCS theory is right and explains an enormous amount about ordinary superconductors, it's simply inadequate to understand the new physics that's manifest in the high temperature superconductors. Okay, thank you.
That was super. I'll open the questions, but I wanted to ask a question here. This formula.
Yeah.
It sounds like it's tunneling, huh?
No, this is thermal activation.
This is not.
So if we went to zero temperature, there would be some other formula, which I can write for you, that would be even more absurd. But yeah, this goes to, of course, this, if I took the temperature to zero, this rate would diverge. That doesn't really happen. You can have quantum tunneling of vortices. Yeah. So this is the energy for a quantum vortex to penetrate the superconductor. Mm-hmm. And so it thermally activates. That's the peak in the activation.
Okay.
If I were to tunnel through it, it would be something that would go like e to the minus the distance it tunnels times the thickness. So it would go like e to the r squared.
Ah, okay, good. Thank you.
Yeah.
Questions?
Hi. So earlier on in the lecture, you showed that resistivity as a function of temperature is the derivative is greater than zero. Then you showed the graph as you approach near absolute zero,
Yes.
resistivity drops down to zero.
Yeah.
Are there any materials that you found which have nonlinear properties at that transitional period, or not monotonically decreasing?
So okay, so there's several things. So first place, there are indeed some materials where the resistivity is increasing as you lower the temperature, and then they go superconducting. Some of the high temperature superconductors do that. So there are, so in typical metals. So typical metals, the resistance comes down and then goes down like this. The high temperature superconductors actually turn out are incredibly bad metals. To plot them even on the same curve, you have to probably scale the curve by a factor of 1,000. Okay, but once you've done that, some of them, and of course the temperatures at which they make transitions are much higher. So I'm scaling everything, but some of them, usually the ones with the highest transition temperatures, still look like this. But you can change the stoichiometry of the material somewhat, and then you get materials that, for instance, do, that was really bad, this. They look like the resistance is trying to diverge, like they're trying to become insulators. In fact, that's part of what's so peculiar about the high-temperature superconductors. They're the world's worst metals. They're right on the verge of becoming insulators, and yet they're the world's best superconductors. Yeah.
You didn't put the high-temperature superconductors on the history there. What are the dates on that? And who figured it out?
Who figured it out?
Who got a theory that would explain it?
Me.
You. And when did you do that?
Last week. Come next week, and I'll answer your question more seriously.
The formula with the time constant, is it experimental?
What?
The time constant formula,
Yes.
is it experimental or theoretical?
So that's theoretical, but there are experiments that have tested it. In order to test it, you have to purposely make your ring really, really small. You have to make it so that the persistent current lasts not the life of the universe, but an hour. Okay? And so to do that, you engineer yourself to have really, really tiny, tiny rings. And you can even get into the regime where you can see the quantum effect that Lenny was talking to. And that quantum effect is actually something I'll talk about next week as well.
How tiny is tiny? Nano?
What's nano? No, not nano. You don't need nano. What was the word that... what? Yeah, but there's a word. Mesoscopic. Mesoscopic.
You can see them optically.
What? Yeah. Yeah.
So going beyond mesoscopic, and you have a couple constants in there, but I don't see the gravitational constant.
Right.
Including that in phrase of question, is there any reason a cosmologist would be interested in superconductivity?
I think there are two answers to that. So first, conceptually, the understanding of superconductivity has totally transformed our way of thinking about emergent phenomena in physics. For instance, the standard model of particle physics is sort of a transcription of the theory of superconductivity. And I'm sure there are further, so for cosmologists, there are even talks of things like superconducting cosmic strings, which are directly analogous to the flux quanta that I've sketched up there. So that's deep. There's also a user's interest, which is that many of the most sensitive measurement devices are based upon the macroscopic properties of quantum mechanics, of superconductors, and so certainly those play a big role in cosmology.
Well, a particular thing which is related to what you said first is as the temperature of the universe came down, it passed through a transition, which was the transition to the Higgs effect.
Right.
Which is basically
Superconductivity, yes.
Superconductivity.
But I thought also the neutron stars are actually superconducting.
Huh?
That's true.
Is that a theory or experimental fact?
So I've been told that.
Me too.
Usually by people boasting about how important superconductivity is for everything. So, take that as you like. Yes?
You mentioned that the resistivity of pure crystals is less than dirty ones.
Yeah.
What about the resistivity of the amorphous form of a metal?
That's a really good question. So the resistivity of amorphous metals is 135 microohm centimeters. Okay, and the theory of that I wrote down. Well, where's my constants? I will get everything wrong if I don't. All right, here we go. Rho Q is equal to 2 pi, no, other way around. H cubed over 2 pi squared e to the fourth m, which turns out to be 135 microohm centimeters. So by dimensional analysis, if nothing interesting was happening in the solid, you would predict that its resistivity should be 135 microohm centimeters. And it turns out that amorphous metals and liquid metals and crappy alloys all have resistivities that are within a factor of 2 of this. Yes?
So this is condensed matter physics. What does that cover, and what are the alternatives?
Yeah, so it means I only lectured for an hour as opposed to 12 hours. So what condensed matter physics refers to is physics of matter that's dense enough that the interactions between the constituents are very important. So it really means the study of solids and liquids and liquid crystals and quantum liquids, all matter that's dense, as opposed to gases. And it also generally refers to materials that you can have in the laboratory, as opposed to, for instance, neutron stars. So it presumably mostly refers to situations where gravity doesn't play a role. Although there are proposals to do very careful experiments on critical phenomena in condensed matter systems on the space station because the gravitational effects mess us up. Yes?
In the Josephson
What?
effect, in the Josephson effect, like the current is changing, so isn't there going to be a changing magnetic field? Is that bad?
In the Josephson effect?
Yeah.
Yeah, so, I mean, there is. So as you apply the voltage, the current oscillates. As the current oscillates, it emits electromagnetic radiation, and you can detect that.
But you said like Meissner effect, like there should be no magnetic field in the superconductor.
So, but it's not in the superconductor, it's in the junction.
Question over here.
Yeah.
I have a question about the type 2
Yes.
superconductors. So you took us from, as you increase the magnetic field, you get to the quantized fields that the superconductor
Do I still
can
have it?
sustain up above, yeah.
Ha.
So if you keep on increasing the field, the number of...
Yeah, so eventually the system will give up the
So at
ghost.
some point-
So here, there's an HC1. So if the field is less than some HC1, you remain in the Meissner state. Then above some first critical field HC1, you go into this, which is called the mixed state. And then finally, above some second critical field HC2, superconductivity gives up the ghost. I mean, ultimately, the currents are too big, the energy cost is too much, the system simply becomes a metal with a magnetic field going through it.
Do we know if that depends on the type of superconductor?
Yeah, so this depends upon all sorts of details about the materials. So the high temperature superconductors turn out all to be strongly type 2 superconductors. Many simple elemental superconductors are type 1 superconductors, but then if you disorder them, if you put impurities in on purpose, which makes them worse metals, but it makes them much better, it makes them type 2 superconductors and much more useful. So there's an example where messing the system up is a good thing to do.
On the type 2 system, when you have a mixed state, the actual organization of where the flux breaks and where it doesn't, is that a function of like the crystal, the material, or is it randomized or what?
Yeah, so that's complicated and there are different answers in different situations. So if the material is very pure, very clean, these defects, these vortices, form a crystal of their own. They organize themselves into what's called an Abrikosov lattice after the theorist that first predicted them. But if there's a lot of disorder in the system, which is the case for most useful superconductors, then these follow some complicated route that's determined by microscopic physics of the distribution of impurities and defects and other nasty details.
Yeah, you said that the conductivity and the lifetime of current is essentially experimentally verified. Right?
Yes.
With these really large numbers. But doesn't the surface roughness and things like that have some effect? I mean, how do you practically get a measurement like
Isn't that amazing? I mean, you know, this is real stuff. You know, things you hold in the hand. You know, you do the Josephson effect, you know, there's solder and there's cracks and there's all sorts of stuff. And the Josephson effect is exact.
Yeah, but how does where does the current flow? It has to maybe not flow in those defects, or it ignores the surface somehow? I mean,
so it's what we call a topological effect. It's an effect that's independent of the details. It only depends on the topology. In this ring, for instance, the fact that there's a ring, if we looked close, we would discover that it didn't look like this, but looked like this, and maybe it had a hole here and there. But as long as it's got the topology of the ring, the current can flow around, the field is trapped, and the persistent current is exact. So, I mean, you're right on. It's really amazing. This is not an abstraction. These are real pieces of material.
So when you're talking about the energy expelled in magnetic field, what is that energy you mean? Like if the system, the superconductors has to spend energy to do some work, like how can it maintain its...
So that's the thing about superconductors. It can maintain these currents, even though it costs an energy. There's no way for it to decay. I mean, picture a ball. There you go. Suppose I had a geography that looked like this. Okay? And I put a ball here. Now, it would rather be here. That's lower energy. But as long as this mountain that stands in between where the ball is and where its absolute minimum of energy would be, it's not going to know about this. It's going to stay here, well, almost forever, or until it learns how to climb this peak. So that's the same idea as what's going on here. So this state with the current going around is like the ball in this valley, but the height of this peak is so enormous that it's trapped here for longer than the life of the universe. I'm happy to answer questions forever, but I wonder if people are being polite. Maybe we can let people leave and then go on with questions, or people are not being polite. Okay, good. If anybody wants to leave, I'll take notes, but yeah.
In the Josephson effect, what is the order of magnitude of the gap, and do we have ionization in the gap?
So you're asking,
it's gone.
It's gone. Okay. Let's work over here. So we had a superconductor here, we had a junction here, we had a superconductor here, we have a voltage, and what we found was that I of t was equal to I naught times cosine of 2 pi nu times t, where nu was equal to 2e over h times v. Okay, now I naught, the magnitude of this effect, hides a lot of complicated physics that has to do with the nature of this junction. The bigger this junction, the smaller I naught is. If I naught is really small, then it becomes too small for us to detect. So you would like these junctions to be pretty small, but that's a practical issue. In terms of this oscillation frequency, it's totally independent of the nature of the junction. And so when I talked about the precision of the effect, in fact, part of what people did was to take two very, very different junctions, one with, I don't know, lead leads and some oxide in between, and the other with niobium leads and a weak link between them with no oxide, and they have exactly the same frequencies.
What kind of order of magnitude is the junction, the width?
It depends on what you put here. So if you put an insulator here, then it has to be a few nanometers at most, probably less. If you put a normal metal there, it can be, well, I don't know, bigger. What's a number? Give me a number. What?
Nanometer, anyway, I think...
Tens of nanometers, certainly. What?
If it's graphene, it has to be.
Yeah, if it's graphene, it can be really far.
Yeah.
Thank you.
These are people that actually do things, rather than just talking about them.
What happens if you put a voltage across superconductor and there is no junction like that? It's just across part of a ring.
Right. So you get a huge current until the voltage goes away, or until you exceed the critical current, but there's no steady state that corresponds to that. It'll be a transient effect of some sort. Yes?
So just looking at the equation,
Yes.
does that mean that at some times the current flows against the voltage?
Yes. Exactly right. So the current oscillates. Sometimes it's going down the voltage, sometimes it's going up the voltage. Very surprising.
In your demonstration, are there any currents being induced in the superconducting material, or is it just
Yeah, so this is what's going on microscopically, which means that around each of these is like a microscopic version of this. So the currents are going round and round these little holes, like that.
Which all adds up to a current around the boundary.
There's also a current around the boundary, that's correct. And, well, so people like this gentleman sitting down here actually image these currents in the laboratory. So you can actually see them.
Are those currents constant, or do they time vary?
No, constant. That's why it just sits there.
I mean, when you're imaging it, it's
They're constant.
no change.
Yes.
If you make a very small tip of some superconductor, you may be able to detect the current. Is that correct?
So
Because you have a Meissner.
yeah, so that's not exactly how what they actually measure are the local magnetic fields, and they do this with one of two ways, either with a small piece of metal where they measure what's called the Hall effect, which is a transverse resistance, so that's called a scanning Hall probe, or with another very small superconducting device called a squid, and that's a scanning squid. So the way they image is by dragging either a very small squid or a very small Hall probe across the surface of the sample.
So again, talking about the type 2s, is it possible to build devices using that, particularly memory devices?
Yes, good. Yeah, so I knew the question would come up about, what the hell is this good for? So, I mean, there's an easy question to that, answer to that, which is it's extremely interesting and it got me a job at Stanford. So from my point of view, it's extremely useful. There are proposals for all sorts of uses of this. You can certainly imagine that superconducting interconnects in computers would be an enormous benefit because there would be no heat generated. You can also imagine, and this is part of I left out the third thing, which was macroscopic quantum coherence. So there are wonderful proposals to use a property of superconductors that I'll talk about next week to build a quantum computer. And if that was possible, that might be extremely interesting. There are some other practical uses of superconductors. They're used in MRI machines. They're used in power grids in hearts of cities. But most of their practical uses are in the future. Yes?
For a type 2 superconductor, the flux tubes are close enough together, and as the radius gets smaller, it decays faster.
Yeah.
They're really close, so they decay over a short time period.
Yeah. So the answer to that's a little bit complicated. There is a time scale of the sort that you've said, which becomes shorter as these come closer to each other. And that's a time scale for these vortices to move around and to adjust to the local conditions. That's called vortex creep. It's very slow, but it's measurable. That's why it's called creep. The time scale for the flux to either leave or to become denser in the superconductor depends on circumstances, and I think it's a little technical. let me punt on that one.
What's the maximum frequency to that?
What?
Gigahertz or what time constant?
Maximum frequency. I think one is interested in the minimum frequencies, and those can be, I mean, it's a glassy phenomenon.
If you want to do computers, you have to go fast. No?
What? No, okay, for use in computers, you want this time scale to be long, and it is long. Yeah, that's not a problem. Yes?
I would assume that the voltage in this frequency expression, the Josephson frequency expression, I would assume this voltage is very low, otherwise it's not practical frequency to measure.
So, okay, I cheated a little. You don't really measure this with an ammeter. You really measure the electromagnetic radiation that's emitted as it oscillates. And then the voltages can be whatever you want. I mean, it just shifts the frequency accordingly. Yeah, so lower the voltage, the lower the frequency. So you can get it in what range, in principle, you can get it in the ranges you want. I mean, obviously, if the voltage is too big, then all sorts of nasty things happen.
Is it possible any metal can become a superconductor under low enough temperature?
That any metal?
Can become a superconductor under low enough temperature?
That's an extremely good question, and the answer to that isn't known. There are fairly compelling theoretical arguments which are so compelling that they're known as the Kohn-Luttinger theorem, but it's not a theorem, which say that metals at low enough temperatures should all become superconductors. However, empirically, people have followed, for instance, copper to extraordinarily low temperatures temperatures that are many orders of magnitude below any natural quantum of temperature, and it refuses to become superconducting. So, okay, anyway, yeah, but I think the answer to that question isn't known for sure.
Is there any in-principle reason why, if you take a superconductor and continue to lower the temperature, it can't stop superconducting?
No, in fact, there are cases where you get reentrant superconductivity. It's usually due to a competing order. You cool the system and it becomes a superconductor, and then it becomes a magnet or something like that. But no, there's nothing against it, and I think it's been observed. I don't remember in what.
When you're talking about high temperature superconducting, what temperature range are you talking about? And is there a limit for higher temperature?
Yeah, so that's a very good question. So there's a practical definition of high temperature superconductor, which means anything that's superconducting at a transition temperature above 70 Kelvin. That's anything that can be cooled with liquid nitrogen to its superconducting transition temperature. There's actually only one family of materials that so far have satisfied that. The highest transition temperature in that family of materials is 150 Kelvin, so that's quite a bit higher. Of course, one of the holy grails of the field is the search for a room temperature superconductor. And okay, well, I hope in a few years I'll have demonstrations with no need for liquid nitrogen.
Oh, that would be sad. It's so nice to watch.
It is nice, it's true.
Okay, I think we should let me go home.
Right. Okay, but if anybody wants to come down and play with superconductors, they're welcome to. And I think my daughter has offered to supervise the demonstrations.
For more, please visit us at stanford.edu.